Okay, so we've been talking about some organic groups here. We've talked about our aldehydes. And once again, the functional group of our aldehyde is the carbon-oxygen double bond with the hydrogen there. We also talked about ketones, which is again our 3-carbon run with the carbon-oxygen double bond there in the middle. So we talked about several things about these guys. First off, again, to name our aldehydes, they will end in Al. You do not need to give, as we talked about, the location of the carbon-oxygen double bond, and that's because of that hydrogen that is there, which means that it will always end up at the end of your molecule, one end or the other. Again, because hydrogen cannot have more than 2 electrons. So the result of that is you don't need to give a number as to where the carbonyl carbon is located. But in terms of numbering any other groups that may be present, that carbon should always be carbon number 1 when you go to sort of number the chain. And that's a little bit different than what we have with ketones, right around 5 or so carbons. We do need to give the location of that carbonyl carbon where the double bond is located. Ketones do end in ONE. And much like what we do with alcohols, alkenes and alkynes or double bonds and triple bonds, when it does sort of make a difference where there is more than one location of where that carbonyl carbon can be, you do need to give the numbers. So with ketones, right around 5 is sort of where that happens, as he has to give the numbers. We do want to obviously give it the priority in terms of numbering the longest carbon chain. So again, whichever way will give that guy the smaller numbers, definitely the way that you want to go. Let's see here. We talked about really several reactions that involved alcohols, which is really how we generate both of these guys. Again, we have our primary alcohol that we can oxidize to an aldehyde. So again, with our primary alcohol, we have something like this. Taking off our 2 hydrogens there and making our double bond, again going to generate our aldehyde. We also talked about that this guy can also further go through an oxidation, and the oxidation of the aldehyde at this point will result in oxygen being inserted right about there to make really another organic group, which is a carboxylic acid. And that would get you something like this here. And the functional group there of our carboxylic acid is this part right there. And we can get a ketone from the oxidation of a secondary alcohol. So again, we could generate that by losing our 2 hydrogens there and making our double bond happen. And we'll go for our secondary alcohol to our ketone. Once again, won't oxidize past that point. So we did talk towards the end there about a couple of tests that you could do to identify an aldehyde versus, say, a ketone. That's the Tollens test and also the Benedict's test. Again, the Tollens test will turn silver color, like a mirror, as a positive sort of result of that. The Benedict's test used copper, which copper goes from the kind of blue color of copper 2 down to kind of, again, the orangey reddish type color of copper 1. And again, that would be a positive test for an aldehyde being there, because it will generate basically our carboxylic acid. Our ketone basically will not. We also talked that we could do really the reduction reactions for all these guys, and that's basically going the opposite way. And when we're dealing with an aldehyde or a ketone, and we're going to do a reduction reaction, that basically means that we're going to add H2 to it. So we'll add 2 hydrogens. And as I talked about at the end there last time, it basically works kind of the same way as how we do the hydration reaction of a carbon-carbon double bond here, and it basically happens exactly at the same carbon bond here, the double bond. The only difference is not two carbons, is a carbon and an oxygen. So when we do this hydration or reduction reaction here, we're going to turn our double bond into a single bond, and that is going to give us a spot to add one hydrogen and the other hydrogen. And again, that will take us back to our secondary alcohol going in the reverse direction. And you could also do the same thing with your aldehyde. You could add H2, and that again is a reduction reaction in both of these cases. And same thing, it's going to basically happen right there. Everything else, again, remember, stays the same. We're going to make our double bond into a single bond. And again, we have now room to put both of those hydrogens on there. And again, that will get you back to your primary alcohol. So the oxidation, as we go from the alcohols to the aldehyde or ketone, is a result of losing the two hydrogens. The reverse sort of reaction of that's the reduction, basically putting the hydrogens back on in the same spot where you lose the two hydrogens. It's basically where they go. Again, one to each of those things. Any questions on that there? We also talked about some other organic groups, I think, along the way. We also talked about thiols, I think, and those are, again, sulfur-containing groups. And although you do not need to name thiols, you do need to recognize the functional group. And we also talked about a reaction that involves thiols, and that is an oxidation reaction that could happen. So if you have a couple of thiols together here, and you basically add them together, it will be the loss of hydrogen in this case, as you do basically the oxidation reaction. And basically, we're just going to take the hydrogen out here and then just squeeze everybody together. So if we do that, we will end up with H2, and we're going to squeeze everybody here together, and that makes, again, a disulfide bond or disulfide bridge between these two. And again, as we talked about last time, what you want to remember is pretty much just take out the H2 and squeeze them together. Again, nothing much changes. So if you just start at the left-hand side, CH3, CH3, CH2, CH2, sulfur, 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 CH3, CH3. So again, you just take out the H2 and just squeeze everybody together. Clearly, that's the oxidation reaction, which again, definition would be loss of hydrogen. Just like anything else, we can basically start with our products here and do a reduction reaction. And just like we put it together between the two sulfurs, when we add the hydrogen back, that's exactly where it's going to break apart once again between the two sulfurs. And this will be a reduction reaction. And that will get us, again, we're just going to draw everything that we got going on. We are going to split it at this point. And what we are left with is this guy will get a hydrogen and this guy will get a hydrogen. And now we got basically our two thiols together. So again, sort of opposites of each other in those reactions. Oxidation basically puts those thiols together, remove H2, reduction. You have a disulfide sort of bridge, which is basically two thiols already together. You add a hydrogen back in and it will basically separate those guys out. Any questions on that one there? We talked about ethers, I think, as well. And ethers have a carbon, oxygen, carbon as the functional group. There's a couple different ways to name ethers. The IUPAC way, which we won't do because I believe your book is rolling with the common way of naming. So we'll go with the common way of naming. And remember, in the common way of naming, essentially, you basically look at your ether sort of group there, and really you just kind of focus in on the oxygen. So we kind of focus in on the oxygen. And in the common way of naming these guys, we just basically look to the left, look to the right of the oxygen, and find the different sort of groups that are there. So that's going to be a methyl group. That is going to be a propyl group, as that is 3 carbons. And in the sort of common way of naming ethers, basically just alphabetical order on the groups, and then you just put ether at the end. So this would be methyl, propyl, ether. Question on ethers, or those are, I think that's what we talked about last time, if I remember correctly. Just a reminder as well that I'm sure you've seen it, but if you have not seen it, up on Canvas, there's sort of a reaction sort of sheet that I made that kind of describes all the reactions we're talking about here in all these chapters here with organic. And I also just in words try to explain, make the double bond a single bond, put this there and that there. So if you haven't looked at it, it's probably a good thing to kind of take a peek at. We'll kind of sort of explain each of these reactions. Obviously, there's some organic worksheets up there as well. So, and some answers to those. So make sure you take a look at those if you haven't done so as well. The most important thing when you are drawing products of reactions is not to get too fancy with it, Jim. So as we talked about a number of times, pretty much kind of what you start with is pretty much like the product. So you have almost 90 some odd % of it there in the actual question. Everything pretty much happens at the functional group part of the molecule. So that's really the only part that will change. And you just got to do the appropriate change, but pretty much leave everything else the same. So what you should be doing is when you look at something like this is, when you go to draw it, pretty much copying what you got over there. Again, just changing the parts that need to be changed. And that's a good approach. Any questions on any of that there? All right. So I don't think we did this one. So why don't we do this one here? What is the product of the oxidation of this guy? Okay, so let's take a look at it. So first off here, we have an alcohol, and we do have a secondary alcohol. And again, why it's important perhaps to look at that sheet, or just in general, try to figure out, what you should make, is sometimes it's easier if you know what you should make to draw it as well. So this is obviously an oxidation of a secondary alcohol. Which means we should end up with a ketone. And so basically we're going to remove our H's right there. You're going to take those guys out. And again, we're just going to draw exactly what is there. So we got a little bit of this, a little bit of that. And again, we're now going to insert obviously our double bond there between the carbon and the oxygen. And that hopefully should match something right below it. It looks like perhaps B would be a winner in that case. That is, by the way, 4 carbons, which is butanone, right? Would be the name of that ketone. Question on that one there. All right. All right, so why don't you do this? If we start with this guy here, which looks like 1 propanol, what are the 2 products we should get there for? I feel like my arrow is in the wrong spot there, perhaps, but we'll see. I feel like my B is in the wrong spot. I feel like that should be B right there. That should be C. There you go. All right, so what are 2 end products you should get there? Draw them up, see what you come up with. So once again, if we look at this, we have the carbon that has the OH group. We also have an OH group, which makes it an alcohol attached to one other carbon, which means it is a primary alcohol. which again means if we kind of understand what should happen, that first oxidation should give us our aldehyde. And again, that second one should give us our carboxylic acid in that case. So it may be helpful to draw out some of these functional groups here. So we'll do our H3C, CH2, COH, H and H. So we're going to do our first oxidation here. And again, remember that is the removal of our two hydrogens. Again, one from the OH and one from the carbon that has the OH group attached to it. Nothing else changes, which means we're just going to copy pretty much everything that is there, except for obviously the two H's we're taking off. And now, as we talked about, we do need to insert our double bond there between the carbon and the oxygen. So the first one that we would end up with is number 3 there. That is then followed by the next oxidation step, which remember will give us our carboxylic acid. So really at this point, if you know it's a carboxylic acid, you just got to kind of turn that guy into the right functional group, which means really the only thing is missing is the oxygen that should end up there. And again, we'll just copy it exactly the way it is. And that will give us, again, our carboxylic acid functional group, which means we should end up with number 4 there when it's all said and done afterwards. Any questions on any of those there? All right, so let's do 2-propanol. Give the products when you do the oxidation and you do the dehydration reaction. So draw out what you should get. I would start with drawing 2-propanol. All right, so let's take a look. We're going to start with our 2-propanol. So we'll just draw this like normal. So OL tells us it's an alcohol. Propanol there tells us it's 3 carbons. So we're going to do 3 carbons to start with. The OL, which is the alcohol, is at carbon number 2, as it tells us there. So we'll end up with this, and I'm going to actually draw out the hydrogen there, I think. And maybe actually I'll draw out all the hydrogens maybe here so we could kind of see it. All right, so we'll just draw out some hydrogens. All right, so we have our 2-propanol. So the first thing we're going to do is we'll do the oxidation of it. So as we talk about, obviously here, this is a secondary alcohol, as that guy is attached to 2 other carbons. That means we're going to take a hydrogen there and a hydrogen there. And once again, everything else will remain the same. And we're going to end up with our ketone, which is, again, what we should expect to happen here. And we'll end up with our propanone here, right? So we have our 2-propanol that goes to propanone, O-N-E. Any questions on that one? Coming to the other, which is the dehydration reaction. Dehydration means we're going to remove water, right? And we're going to remove water coming this way. So I'll just put minus water here. So that means to remove the water for the second one, we're going to definitely take the OH off, right? And that's how water attaches. Then we need to take a hydrogen off. And in this particular case, does it matter what hydrogen I take off from the carbon to the left, carbon to the right? It doesn't matter, as they both have the same number of hydrogens. The only hydrogen I should not take is the one that's actually circled, right? I should not take that hydrogen. It does need to come from a carbon to the sides of it. So why not? Let's just grab that guy right there. And that means that we will end up with here. We will end up with this. And obviously where we remove water, we will then need to put a double bond in its location. Obviously we go from 2-propanol in that case to alpene, right? ENE and alkene, right? Double bonded action happening there. Any question on those two reactions? Hopefully you can again start seeing a pattern that what you are drawing looks very similar to what you started with. So again, don't get too fancy with it and just change the functional part of it to get what you need. All right, let's take a look at each of these here. We'll change this to ethanol, AL. All right, so for each of these, if you hit it with the Tollens reagent or the Benedict's reagent, your choice, whichever one you have handy to use, what is the product you should get out of each of these? So why don't you try that and see what you come up with. Okay, so let's take a look. So remember that these tests, as we talked about earlier, really are for our aldehydes that get oxidized to our carboxylic acids. So that is sort of where we end up there, carboxylic acid. So we will look at butanol. Al means it is an aldehyde, and it has 4 carbons, 2, 3, and 4. So it should look something like this. And that means if we oxidize it once again, pretty much that's the only thing that's going to change. We're going to make it into our carboxylic acid. So we will go straight through here, exactly the same. And if I don't run out of room there, we'll put my oxygen in there, and now we'll have our carboxylic acid. So we go from butanol to what is known as butanoic acid. Okay, which is obviously a carboxylic acid. Question on that one there. Ethanol, Al, is obviously as well a aldehyde. It's a 2-carbon aldehyde, which means you got to put that group there at one of the ends, and then we should have 3. Once again, this guy will oxidize into there, and that will get us CH3COOH, and we'll go from ethanol to ethanoic acid in that case. Last one is a ketone. Just from the name, it's a ketone. So it's ethyl methyl ketone. That's really the common name for a ketone, which, by the way, if you needed to do so, you would do that. And then we have an ethyl, which probably is a couple of carbons, and a methyl, which is 1 carbon here. And that's also known as butanone, right? Which is our 4 carbons right there. We're going to oxidize this and not going to get anything, right? So we'll not do it because it's a ketone, kind of missing the hydrogen there on that carbon to sufficiently allow it to do that. Any questions on aldehydes, ketones? All right, so I do want to talk about 2 reactions that involve aldehydes and ketones, and what happens when you add alcohols to an aldehyde or a ketone. So if you take a aldehyde to start with, and we'll just take a nice simple aldehyde, well, ethanol as we started here, and if we add to it 1 alcohol, we'll just do how about methanol here? We'll add a little methanol to it. So what's going to happen is, in this particular case, the alcohol will add kind of like, it will do pretty much like an addition reaction. And how the alcohol adds is it will add actually in 2 parts. One part that will add is the hydrogen part, which is like H+. And the other part that will add is what is left there. And that would be, actually we'll do this oxygen carbon group here. This guy's really negative. This guy's really positive. And that's kind of important because what's going to happen is it's going to attack pretty much the carbon-oxygen double bond, which is probably not a surprise since that's kind of where everything happens. Now, if we think about that carbon-oxygen double bond, it is a polar group right there, with the oxygen being more negative and the carbon being more positive. So this helps us understand perhaps where things end up. Opposites attract, right? So the hydrogen is actually going to come in to where the negative part is, and this oxygen carbon group, which is actually negative, will come in towards the positive carbon. Now, can I just add both of those to the carbon-oxygen double bond? I cannot, because again, too many bonds. So just like all the other sort of addition reactions that we kind of do here, before we do any of that adding in, we got to make room for it. So we got to get rid of the double bond. And once again, nothing else is going to change. We're just going to get rid of the double bond. So that is what I'm going to draw in this case. We're going to do this. We're going to make that double bond into a single bond, and we still have that hydrogen. Now we have room for each of those parts of the alcohol to come in. And once again, the positive hydrogen will end up at that negative oxygen, and the negative oxygen carbon group will end up over there at that carbon. Any questions on that there? What we just made here is what is known as a hemiacetal. So a hemiacetal is made from the addition of one alcohol to an aldehyde. And what the main components of a hemiacetal is, when you look at the carbon that had like that OH group originally, it should have a OH, it should have an oxygen carbon group, and it should have a hydrogen attached there. So those three things are sort of necessary for it to be a hemiacetal. Again, it should have an OH group, it should have a hydrogen, and it should have some type of oxygen carbon type of group attached, which is what all three of those have. So if you add one alcohol to an aldehyde, you will get a hemiacetal. And if you added two alcohols to that aldehyde, the first thing that would happen is the first alcohol would add just like we just did there, and you would have your hemiacetal. And then what would happen is your hemiacetal would then add the second alcohol. So if I redraw what we just made, and that is not what we just made, so let me fix that a little bit. All right, so we have a H there and an oxygen carbon. So if I were to add another alcohol, could be the same alcohol, could be a different one, but we'll just use the same alcohol. In this case, we're going to have the same sort of addition. What's going to happen in this case is, again, our hydrogen is going to come in, and our oxygen carbon group is going to actually come in. So a little different process happens here, and how it happens, not super important for us. But essentially in this process, what happens is we will lose water. So water will come off. And how water comes off is it will come off as the hydrogen here and the OH right there. So the OH and the H will make our water. A lot more complicated than what I just did there, but that is essentially what will happen, is that water will come off. When that OH group leaves, it is going to leave us that carbon that is still going to be more positive in this case, because OH is OH minus. So as it leaves, that carbon is going to become more positive. And what's going to happen is, after we lose the water, that's going to allow the oxygen carbon group to come into its place. So we're going to take off basically the OH as it makes water, and that's going to, in reality, make the carbon that's still there more positive, and that negative oxygen carbon group is going to be attracted to it, and it's going to come in. So at this point, what we would have is exactly what we started with, except that obviously we got rid of our OH. So we'll have everything looking exactly the same. And now that we made room for it, essentially, we will put on the second oxygen carbon group right there. And this is what is known as a acetal. And that is what you get when you add two alcohols to an aldehyde. If you add just one, you get the intermediate step of the hemiacetal. If you add two, it goes one more, and you will get what is known as the acetal. What are the key components of an acetal? It's very similar to the hemiacetal, except it doesn't have the OH, hence hemi-OH. It has two of these oxygen carbon groups, and it has a hydrogen. So that is what makes it an acetal. It has those two oxygen carbon groups and one hydrogen. Yeah. So it's got both of those things there. Any questions on that? So again, two alcohols takes you all the way to the acetal. One alcohol you stop halfway through and you'll have the OH. Any questions on that one? Now, our friend, the ketone does pretty much the same deal because it has the exact same carbon, oxygen, or carbonyl group. So if we did this exact same thing with the ketone, we will get something that's very similar. So let's take a look at that here. So we'll start with, again, a pretty simple ketone, I think. So we'll just do this guy here. And once again, if I take my ketone and I add one alcohol, again, it doesn't matter what the alcohol is, we'll just do a small one here since I don't want to run out of room. The first thing that's going to happen is the exact same thing that happened with our aldehyde. We're going to break this double bond and make it into a single bond. So if we do that, we will have everything that looks the same, except again here, we're going to break the double bond and make it a single bond. And just like it did with the aldehyde, the alcohol will add the same way. You will have the hydrogen that's technically more positive that will be attracted to the negative oxygen. So that hydrogen will end up there. And you will have this oxygen carbon group, which is more negative. That's attracted to basically the carbon, and it will end up right about there. Yeah. And that looks very similar to what we have above, right? And it has a similar name. It is what is referred to as a hemiketal in some circles. And that is because it comes from a ketone. Yes, the other one comes from an aldehyde. Although some books will call them both a hemiacetal. Some books will call them both the same thing, but some books will distinguish between them. But technically, it's a hemiketal because it comes from a ketone. It has the same components as a hemiacetal, except one really critical difference is in a hemiketal, it has an OH group, which is again why it's called hemi. It actually has the oxygen carbon group, but it has no hydrogen. So unlike up here where we have that hydrogen, no hydrogen here because it started out as a ketone. So we have a carbon there instead. So that's the main difference between those two is obviously the lack of hydrogen in this particular one because it started out as a ketone. Any questions on that there? So you can think of it just like above, it's kind of like halfway there. So if I added one alcohol to a ketone, I will get this hemiketal, and very similar to what we have above. If I add a second alcohol to it, it will then react with our hemiketal. And I'm going to redraw it, I think, on the next page. So if I take my hemiketal and I add again one more alcohol to it, it's going to do pretty much the same move as the other one. We are going to lose water here. So the water is going to come out the same way. We have our hydrogen and our oxygen carbon group. So once again, we will take our hydrogen, we'll take our OH, and that is what's going to get us over here, some water, maybe. And once we do that, this negative guy is going to go in its place, and we will get exactly the same looking thing here. Again, nothing changes except get rid of the OH and replace it with the other oxygen carbon group. And this is what is sometimes referred to as a ketal, again, because it comes from a ketone. And it has basically two oxygen carbon groups, which basically come from the alcohol. And it has, once again, no hydrogen. So two reactions that basically aldehydes and ketones undergo, and they're pretty much the same reaction in each, is if you add alcohols to them, you'll get either a hemiacetal or a hemiketal. If you add one alcohol, if you add two alcohols, and again, it doesn't have to be the same alcohols in each case, you will end up all the way across there where you won't have any OH groups, and you'll have either the acetal or the ketal. Any questions on that? So if I had this one, for example, and I added this to it. Okay, so let's take a look and see. So we have a ketone, obviously, and we have an alcohol. So what we should know is this is pretty much our center of activity right about there. And again, to help you remember maybe how this thing comes together, again, the alcohol will add that, and it will then add, obviously, this part separate. And the way, again, it's going to sort of end up in this case is if you think about the original guy here, this guy's more positive, this guy's more negative. H is really H plus, and this is really a negative guy. So again, opposites is where things are going to basically end up. But as we talked about previously, we can't just throw it on there. We do have to make room for it. Nothing else is going to change other than we do need to make room. So we're going to single bond up our double bond there. And that means we should just copy exactly what I see, which looks like this, looks like this, looks like this, looks like this, looks like that. Less than 5 seconds, I have pretty much 90-some-odd% of my structure drawn at this point. So all we have to do now is place those things in, kind of like our addition reactions. So again, our hydrogen will end up there, and our oxygen carbon group will end up right about there. And that will make that a hemiketal, right? As it started out as a ketone. Any questions on that? What's that? You don't have to worry about naming it for us. That's a good answer, I think, right? So yeah, so you don't have to name these. You do have to recognize that it is a hemiketal, for example, or a hemiacetal or a ketal or an acetal, and you do need to be able to draw it, obviously, but you don't have to do the naming. Yeah. The answer would be, I don't know. So I don't want to know about naming it either. So other question. Obviously, if we were to continue on here and we added one more alcohol, what would happen again is our OH would come off, right? And then we would take the oxygen carbon group from the alcohol and basically put it in the exact same spot as we took the OH off. And that would take us all the way to the ketal. Question on aldehydes, ketones, chapter 12. So, all right, that is chapter 12. We are off to the final chapter of organic, provided I can find it. Okay, let us take a look here. So chapter 14 is pretty much everything else. So we have carboxylic acid, we have esters, amines, and amides. So we have some nitrogen containing groups, which is our amines and our amides, and our carboxylic acids, which we saw, and our esters, which kind of look like carboxylic acids as well. So let's start with the carboxylic acid. So the carboxylic acid, the functional group is what we saw when we were doing those reactions a second ago. It is the carbon-oxygen double bond and the OH. Once again, sometimes the formulas it's written COOH. So again, if you kind of see that, that is the carboxylic acid group. And it actually has two polar parts to it. It has the carbon-oxygen double bond there, which is positive and negative. And it has our negative and positive polar OH group there. This is going to give a carboxylic acid, as we'll talk about, some pretty good properties, including things like it is one of the few things that can beat alcohols in terms of boiling points, because it could do a lot of hydrogen bonding between both the OH group that it has and also the carbon-oxygen double bond can participate in some hydrogen bonding. So it's one of the few things in terms of things like boiling points and melting points that could kind of beat an alcohol. And alcohol is usually the kind of champ in terms of those things, but this guy can actually do it as well. Now, because of the carboxylic acid group, what happens is when we're talking about sort of that hydrogen bonding aspect of it, when you get a couple of these guys together, we could have some hydrogen bonding happening there. We could also have, badly drawn here, some hydrogen bonding there as well. And again, that allows it to really be bonded to itself pretty strongly. And that again is why it actually will have a much higher boiling point than alcohols, because of the ability to sort of hydrogen bond with itself pretty strongly in each of those cases. We named these guys, as we saw there, with OIC acid is pretty much how we go about naming carboxylic acids. There are some common names for carboxylic acids. So this is 2 carbons, and that is based on ethane, and that is known as ethanoic acid, is the really formal name for it. Its sort of common name is what we call acetic acid. And sometimes people just refer to that as vinegar, right? So all the kind of same deal happening there. It's a major component of vinegar is acetic acid. Next to it is propanoic acid. And if we count carbons just like normal, 1, 2, and 3 carbons. So that's based off of propane. And again, adding the OIC acid to the end of it gives us propanoic acid. Propanoic acid is kind of this common name, sounds very similar. Kind of like our aldehyde, we have our benzene ring, and once again, with our carboxylic acid group there, it will also be kind of off the benzene ring, so very similar to what we saw with the aldehyde. And that is what is known as benzoic acid, OIC acid, again, based off of benzene. Once again, if you were counting, or if there was something else attached there to the benzene ring, although we don't need to give the number of where that thing's located, where it is attached would definitely be carbon number 1, again, for the ring, if you had some other groups attached. By the way, do we need to give the location of where this group is attached? And the answer is we do not, because much like an aldehyde group, it's got the hydrogen at the end, which means it can only end up at the end of the molecule. So it can only end up at the end of the molecule, much like the aldehyde, because of that hydrogen that's at the end. And that means we don't really need to give the location of where the carbon-oxygen double bond is located like we do with some other things. But just like everything else, it does take the priority in terms of naming or numbering. So it would be carbon number 1 if you had other things attached. So wherever that carboxylic acid group is at, that carbonyl carbon where the double bond is located would be carbon number 1, but you do not need to incorporate it into the name. So our simple ones here are methane with 1 carbon gives us methanoic acid. Again, you just kind of drop the E, add OIC acid to it. Ethane, drop the E, ethanoic acid here as it has 2 carbons. Once again, if you had something attached, like say this, we would still do our normal sort of procedure, which is not change the slide. We would come back here and we would count our longest carbon chain. Once again, obviously, it does need to include the carboxylic acid group there. So that's going to be a 1, 2, and 3, which means it's based off of propane, which means it's going to be propanoic acid. Now, again, although we don't need to number it or name it use the number in the name, that would be carbon number 1, which means that carbon number 2, that is where we would find our chlorine in this case. So we do need to use it for our numbering of other things that may be there. So that would give us something like 2-chloral propanoic acid in this case. Yes. Any questions on that there? Once again, this group has got to be on one side or the other because of that hydrogen that it has at the end. So here's a couple of other ones here pre-highlighted, which is nice. So we have 1, 2, 3, 4 carbons, and that's going to be based off of butane. Once again, we have our carboxylic acid group right there. So that's going to become butanoic acid. And here we have a methyl group located right here. Again, as I mentioned, although you don't need to incorporate it into the name, that definitely will be carbon number 1, which means, as we can see here, by the time we get to our methyl, it's going to be carbon number 3, and that would be 3-methyl butanoic acid. Here's our benzene ring, which is highlighted. And again, it has the carboxylic acid group hanging off of it, which means that the base of the name is our benzoic acid. Once again, here we do have 2 groups on the benzene ring, and that means we're going to have a dichloral since they're both the same group. Now, in terms of the ring, where the carboxylic acid is located, again, would be carbon number 1. And just like we've talked about a number of times up to this point, we want to go clockwise or counterclockwise in this case because it doesn't matter because there's double bonds either way you go. But we do want to go whichever way gives us a smaller number for those groups. So clockwise here would give us a 2 and a 3. Obviously, counterclockwise would give us a larger number. If we went in this direction, we would end up with a much larger number. So that gives us our 2 and our 3 dichloral benzoic acid. Any questions on those names? Here's again a list of some common names. I would say probably these 2 you should be probably familiar with. Formic acid, which is methanoic acid. Acetic acid for sure, people use all the time. It has basically the component of vinegar, which is ethanoic acid. So I would say those 2 that I circled, you should have familiarity that when they say formic acid, it's really methanoic acid, or acetic acid is ethanoic acid. I would say probably won't come across too much of these couple of common names. So when we go to name things, we will use the IUPAC way of naming, but just so you remember those first 2, because people very commonly still use those 2 names a lot, especially when you're dealing with acid and bases. They kind of pop up a lot, by the way. I think we might even talked about acetic acid when we did acid and bases. And so now you know it's really an ethanoic acid and really a carboxylic acid in that case. So here's formic acid. Irritates the skin. That doesn't look pleasant, right? And obviously that acetic acid is that sort of sour taste that you have for vinegar. So let's do some naming here. Write the IUPAC name for this guy. And why don't we also do, let's do this one here, maybe. Let's give the name of that. Why don't you also draw, let's do 3-chloral 4-methyl heptanoic acid. Okay, so let's take a look. We'll start with the pre-highlighted one. That seems easier. We got 1, 2, 3, 4, and 5. I'm assuming this one down here is showing it is 1, 2, 3 only. So obviously the 5 there seems like the longest carbon chain. Obviously, it does need to contain the carboxylic acid, which obviously we see there. So 1, 2, 3, 1, 2, 3, 4, 5. That's going to give us a base of this name of pentanoic acid. That means that really the only thing that is a group is the line that's sticking out there. Once again, a reminder that this over here is our functional group, right? So that's the carboxylic acid part there. So that OH is not a group. It is actually part of the functional group that is there. So it's not some type of separate group that's sitting there. A line with nothing on it is a methyl group, right? So that is a methyl. Now, in terms of numbering, where our carbon-oxygen double bond is located does need to be carbon number 1, which means it looks like our methyl group there is at carbon number 2. And that will give us a 2-methyl. I started way too far out. Methyl pentanoic acid there. Yeah. Any question on that name? Looking at the one I drew, we have also, looks like 5 might be a winner. We could get 5 actually coming this way. 1, 2, 3, 4, 5. We could actually get 5 starting up here as well. 1, 2, 3, 4, 5 if you wanted to. So again, you really can choose either way. Whatever way looks good to you. So I'm going to take, I think, this as my 5. And once again, all of that really is the longest carbon chain and the functional group together, as the back end here, once again, is our functional group. That means that we do have a 2-carbon group hanging out there, but we do have 5 carbons, which again means I have pentanoic acid. That's going to be carbon 1, where my functional group's located. Carbon 2 and carbon 3 is where we will find our ethyl group, right? So that would be 3-ethyl pentanoic acid. Any question on that one there? Now we're going to draw this guy. So much like everything else we draw, we always want to work backwards. So the oic acid is a big hint that I have a carboxylic acid happening. The heptane part is 7 carbons. So that's what I'm going to start with. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7. Now, it is a carboxylic acid group, so you could put it at either end, but it does need to go at the end. So I'm going to put mine over here on the right-hand side, which means I will finish my sort of functional group there that looks something like that. That takes care of a good shot of the name there. Now we just have groups that need to be attached. So because I put my functional group on the right, that means definitely for me, that is carbon number 1. Which means carbon number 4 would be 2, 3, and 4 would be right about there. And right there is a methyl group. That also means that carbon number 3, which would be 1 before that, there is a chloral group, right? And now everything else here will just be hydrogens to get me to 4 like normal. So this is going to be 2 hydrogens, 1 hydrogen only there. 1 hydrogen only, maybe no hydrogens, maybe come back. I hope we'll remember what I was drawing. I don't know. Yeah, there it is. We're on that slide with like nothing there. So we're gonna try that mega memory here. Let's see. That was 7 carbons, I believe I had going on there. 7, and I had my carboxylic acid there. I think I was saying something like 1, 2, 3, and 4, and that was my methyl group, and that was my chloral group, and now I was adding hydrogen. So let's try that again. 1 there, 1 there. That was the part I didn't like after that. 2 there, 2 there, and 3 there. Yeah, so that is, I think, what it should look like. Obviously, this is condensed formula. If you were going to do some line structure, still start with the 7. So 1, 2, 3, 4, 5, 6, and 7. And obviously here we do need our you could do this and that move right there, which will give us our carboxylic acid at the end. That obviously would then be carbon number 1 for me, which means 2, 3 would be here, which had the chlorine, I think. And then number 4, which would be here, had the methyl, right? So it looks something like that along the way, yeah. And obviously, if you put it on that end, you can have it going up if you like, yeah. Other questions or questions on those drawing carboxylic acids there? All right, let's take a look at a couple more maybe here and see. Okay, let's take a look. Once again, this should jump out at you as a carboxylic acid. We're going to look for our longest carbon chain. And again, you can get it 2 ways. You can just go straight here, which is 3. You can also obviously start at the top and hang a right there and get 3 as well. So 3 is based off of propane. It's a carboxylic acid, which means it's propanoic acid. That means we do have a methyl group hanging right there. And since this has to be carbon number 1, that means our methyl is hanging out at carbon number 2. That gives us a little 2-methyl propanoic acid action happening there. Any questions on that? Over here, I'm going to go with the big benzene ring staring at me in the face, and I then see my carboxylic acid hanging out there as well. So our base of our name is going to be based off of benzene. That's going to be a little benzoic acid. We do have a bromine group hanging there, and once again, that carbon right there does need to be carbon number 1. Going clockwise here should get us the smaller number. Once again, if we did go the other way, that would be 2, 3, 4, and 5, which is obviously a much larger number. So that is a 3 bromo benzoic acid. Questions on those 2 there? Let's take a look at one more here then maybe to finish it out with. Draw the line structure there, and you can do the condensed if you like. 4. Okay, let's take a look. So the highlighted portion, nice. It says oic acid. So again, that means we definitely have our carboxylic acid group. Hexane basically right there, which tells us we're going to lay up 6 carbons. So I'm going to do condensed first. So 3, 4, 5, and 6. Your option left or right as to where you put that functional group. I'm going to put it over here on the right. That takes care of pretty much all that. That means that's going to be carbon 1, which means my carbon 4 is right about there, which will be our chlorine. And now we'll fill in the rest with our hydrogen. So 2 there, 2 there. It's got 3 lines, so only needs 1. 2 and a 3. Any questions on the condensed formula there? Line, same deal. We'll go 1, 2, 3, 4, 5, and 6. I think 1, 2, 3, 4, 5, 6. In this case, I will put my OH there, and that's going to put my carboxylic acid group at the end. That also obviously will make that carbon number 1 for me, which means 2, 3, and 4 would be right about there. Yeah. Any questions on how to draw them, name them? Good times had by all. Yeah. All right, we will lay it up there for here. Let's talk about a couple things